Okay, so today's lesson is going to take a look at some things that affect the equilibrium. So we've been concentrating mainly on doing calculations with equilibrium, how to calculate KEQ, and how to solve for various unknown concentrations. Today we're going to look at a bit more theory behind the equilibrium. What are some factors, what are some outside things that can take place that can cause this equilibrium to shift? So when a reaction reaches equilibrium, we know that the rate of the reverse reaction equals the rate of the forward reaction. So they get to a point where these forward and backward are occurring at the same rate. In most cases, equilibrium is a delicate balance. So if the conditions change in which the reaction is taking place, this can disturb that delicate balance. And what it does is it causes the equilibrium to shift. Okay, so if you change the conditions of the reaction, then the equilibrium has to adjust to that change. So the change may cause the reaction to no longer be in equilibrium. And the reaction will have to shift in order to reach a new equilibrium. So if the reaction shifts to make more products to reach equilibrium, again we say it shifts to the right. Okay, so to the right means it's shifting in the forward direction. Okay, so if it's moving in the forward direction, it's making more products. So that's a shift to the right. The net reaction is now from left to right. Okay, so here's kind of our basic idea. Reactants on the left, products on the right, and the double arrow is just showing that it's going both directions. So what are some factors that can cause a stress to the equilibrium? Well, one is if you change the concentration of any of the reactants or products. So changes in concentration. Okay, another thing would be changes in pressure or volume. And the third would be changes in temperature. Okay, so I'm just going to clarify that these first two changes, the KEQ value does not change. Okay, so if you have a change in concentration of one particular substance in the reaction, that's going to affect the concentration of something else, and therefore the KEQ stays the same. However, if you remember, whenever we were given a KEQ value, it was always given at a particular temperature. So a change in temperature will change the KEQ. Okay, so these are the three identified stresses. We're going to look at each one individually as we go forward. Okay, so the first thing we have to look at is something called Le Chatelier's principle, and this is just a rule that kind of governs how this equilibrium shift takes place and why it happens. So this says this rule allows us to predict which direction an equilibrium reaction will move when there is a change in concentration, pressure, / volume, or temperature. Okay, so if any one of these three things change as the if any of these three things change for the reaction, how does the reaction shift to reach a new equilibrium? So Le Chatelier's principle says if a stress is applied to an equilibrium system, the system changes in a way to counteract the stress so the system can reach a new equilibrium. Okay, and we know the stresses, we've identified them already, are the change in concentration, pressure or volume, and temperature. So let's look at each one of those stresses and see how the reaction counteracts the change. Okay, so we're just going to look at kind of a standard reaction, reversible reaction, and we're just using letters to represent our reactants and products. So the situation number one says, let's say more of reactant A was added to the reaction. Okay, so we all of a sudden have more of this particular reactant. Which way would the reaction shift to counteract this change? Okay, so Le Chatelier's principle is saying that whatever change occurs, you're trying to counteract that change and bring the situation back to equilibrium. Okay, so the answer to this is that the equilibrium shifts to the right. Okay, so why would it shift to the right if we have more of the reactant? Well, it has to now proceed more in the forward direction to use up that extra reactant and make more product in order to reach that balance again. In other words, the extra amount of A is used in the forward reaction to make more products. Okay, so a good kind of analogy or example to think about, one that we can all probably picture, is imagine you have a closed jar of water. Okay, so nothing's entering, nothing's leaving, and in this closed jar, eventually the liquid water is going to start to evaporate. Okay, so molecules will be leaving the liquid state and entering the gas state. So they're going to become water vapor. So that'll go for a while until the point at which you've got enough vapor molecules that some of those start to condense and go back into liquid. So that at some point reaches an equilibrium, right, where the number of gas molecules going back to liquid is equal to the number of liquid going to the gas state. So they reach an equilibrium. Okay, and that reaction will just continue at that equilibrium as long as nothing has changed about the reaction. But if, let's say, just like we did here, we change something. So let's say we all of a sudden take some of the gas molecules out of there. Okay, so we take some of the water vapor out. Well, now that reaction is going to have to counteract that change. So now it's no longer at equilibrium because some of the gas molecules have been removed. So now, in order to counteract that, it's going to have to produce more gas molecules in order to get back to its equilibrium. So it has to make a shift in order to reach that equilibrium again. So that's the same concept here, right? Whatever change takes place, you have to counteract that change and get back to your balance point again. Okay, so this is just talking about excess reactant. We're going to look at some other possibilities. So when there's excess reactant, more reactant, you get a shift to the right. We got to use up that extra reactant and make more product so that we're at equilibrium again. Okay, so now let's see, what if the amount of reactant B was decreased? So now instead of increasing So now instead of increasing a reactant, we're decreasing a reactant. Okay, so in this case, we're going to see a shift to the left, the opposite scenario. Okay, so now we're going to see more the reverse reaction. And the reason for that is we need to produce more B of the reactant B in order to reach that balance again. Okay, the next one is the amount of C, product C was increased. Okay, so we now have more of one particular product. So that will also cause a shift to the left, the reverse reaction, because we want to use up the product C. Okay, so we're just trying to counteract whatever change has been made to reach equilibrium again. So here's a problem with actual chemicals, with actual compounds in it that we can look at. So we've got nitrogen gas reacting with hydrogen gas to produce ammonia. We've seen this reaction quite a few times before. So this one's saying if more ammonia is added to the reaction vessel, in which direction will the net reaction shift to reach a new equilibrium? So it's our product that we have more of, okay? So if we have more product, we have to use up that product to get back to our equilibrium point. So we're going to have to shift this way, go in the reverse direction. So shift to the left to use up NH3. Okay, so that's kind of how it works if you alter your reactants or your products. Let's look at the next stress, which is a change in pressure. Okay, so changes in pressure do not affect concentrations of liquids and solids. The reason for that is because their particles are already very close together, so they're not compressible. So a change in pressure doesn't affect a liquid or a solid. So it's the gases that we're focusing on here. So concentrations of gases are greatly affected by changes in pressure or volume. So if we see an increase in pressure, this shifts the reaction toward the side with fewer molecules. Okay, so that means it's shifting toward the low pressure side. So how do we know what side's high pressure and which side is low pressure? So it's simply based on the number of molecules that you have on the reactant side versus the product side. So if we look at this particular example, you're just looking at the coefficients in the balanced equation to tell you how many molecules there are. So there is only one molecule of N2O4, whereas there's 2 molecules of NO2. Great. The more molecules there are, the higher the pressure is going to be. So this would be your low pressure side, and this would be your high pressure side. So increasing the pressure will shift the reaction to the left in this particular case, because there are fewer molecules on this side. So again, think about this according to Le Chatelier's principle. We're trying to counteract the change that has taken place. So we've increased the pressure, so we want to counteract that. We want to decrease the pressure and bring it back to the equilibrium. So we're shifting. If the pressure has gone up, we want to shift towards the lower pressure side to make it back to that balanced point of equilibrium. So you just need to identify which side is low and which side is high in order to figure out which direction it needs to shift. So in this particular example, it shifts to the left because the left side has fewer molecules and therefore a lower pressure. Okay, so you can imagine that a decrease in pressure will just do the opposite. Okay, so a decrease in pressure, this shifts the equilibrium toward the side with more molecules, right? You're trying to increase and offset the change. So decreasing the pressure in the reaction above will shift the reaction to the right towards the high pressure side because there are more molecules on this side. So let's look at another example just to give this a try. For the equilibrium system below, predict the direction of the net reaction if the pressure is increased and if the pressure is decreased. So notice in brackets it says here, make sure you consider only the gas molecules because pressure is not going to have an effect on the solids or liquids. So you'll notice we have a solid on the reactant side and a solid on the product side. We're not factoring those into our total count of molecules because they're not affected by pressure changes. So we're just focusing in on the gases. Okay, so we've got 3 molecules of gas here. And we've got 2 molecules, because we're not looking at this one, we're just looking at this one, 2 molecules of gas over here. Okay, so only the gas molecules. We're not looking here. So that means that this is our high pressure side, and this is our low pressure side. Okay, so if we increase the pressure, we want to counteract that increase. So we want to shift towards the low pressure side. So we're going to shift to the right. Okay, if pressure is decreased, we want to counteract that decrease and shift toward the high pressure side. So shifts to the left. Okay, so the right and left are not connected to the increase and decrease. They're connected to, each reaction will be different in terms of which side is high pressure and which side is low pressure. So they're always trying to counteract the change. So if the pressure increases, it shifts to the low pressure side. If the pressure is decreased, it shifts toward the high pressure side. Okay, finally, let's just look at how changes in temperature affect equilibrium. Okay, so we're going to look at endothermic and exothermic reactions. So here we have endothermic reactants, okay? And in an endothermic reaction, you're always going to see energy or heat kind of as a reactant, right? So you'll see that on the reactant side, and you're also going to see this delta H will always have a positive value in your endothermic reactions. Exothermic is the opposite. Okay, so you have your reactants, and then you'll see energy or heat as a product, okay, because it's releasing heat. So you'll see that your delta H has a negative value. So the reaction here, N2O4 plus heat produces 2NO2. You notice here heat is a reactant. So that makes it this an endothermic reaction because that's telling us that heat is being absorbed. Okay, so let's just take a look here at this reaction and see what's going to happen if the temperature changes. So just like in our other 2 stresses that we looked at, the pressure and when you change the amount of reactants or products, we're still trying to counteract the change. So it's good to identify in these exothermic and endothermic reactions which side is the hot side and which side is the cold side. So whichever side the heat is on, we're going to identify as hot. and the other side then is cold. Okay, so if you add heat to a reaction, so if more heat has been added, that you want to counteract that added heat and shift toward the cold side. If you cool the reaction, then you would shift more towards the hotter side. So it works the same way. You're still counteracting whatever change has been made. So in terms of these colors, it's telling you that this gas is colorless and this gas is brown. So we can tell how the reaction has shifted based on the color change. So that's all these colors are referring to. So this says if the reaction is heated, the gas turns brown. So the equilibrium shifts to the left. Okay, so that change of color to brown is telling us that I screwed that up. Okay, so sorry, if the reaction is heated, so we've added extra heat, so we're going to want to shift in order to counteract that extra heat. So we want to shift towards the cold side. So we're actually going to the right. Sorry, so if the reaction is heated, the gas turns brown, so the equilibrium shifts to the right. Okay, so the color brown is just telling us that we're shifting towards this side. Okay, and that's going to cause more NO2 to be produced. So the reaction shifts to the forward direction to use up the added heat. If the reaction is chilled or cooled, the gas turns colorless. So that's telling us we're shifting this way. It's an indication that we're going in the reverse direction. So the equilibrium shifts to the left, okay? And it's shifting to the left because it's gotten cooler, okay? So we want to counteract that change by shifting towards the hotter side of the reaction, okay? This colorless thing is just telling us that now we're seeing more of the colorless gas being produced because we've shifted in that direction. So the reverse reaction is exothermic. The forward reaction is endothermic, the reverse reaction is exothermic, because if you're going this way, then heat becomes a product. It's being released. Okay, so you're still always looking to counteract the change. So here's an example. We've got N2O4 plus heat produces 2NO2. So same reaction, really. So we've got our high temperature, or this is our hot side, and this is our cold side because the heat's on this side. So chilling the reaction causes the reaction to shift in the direction that does the opposite, produces heat. Okay, so if we've chilled it, if we've made it colder, it wants to shift towards the hot side. For temperature changes, remember two things. If a system is warmed, the system shifts to try to correct itself. Okay, so if it's warmed, it goes in the cold direction. If the system is cooled, the system also shifts to correct itself. So it goes in the hot direction. Okay, so the final example that we're going to look at is we're going to look at a bunch of scenarios where we change all three different things. So we're just going to look at them one at a time. So what would happen if you've changed the amount of reactants or products, if you add or remove heat, or if you increase or decrease the pressure? How does it affect this particular reaction? Okay, so a few things we should identify before we ask ourselves those questions is which is the hot side, which is the cold side, which is the low pressure side, which is the high pressure side. So in terms of low and high pressure, that one's pretty easy. There's only one molecule here and there's two here. So here's our low pressure side, here's our high pressure. Okay, Now, you'll notice you don't see heat as a reactant or product, but you're given a delta H value, and the delta H value is positive. Okay, so a positive delta H is endothermic. Okay, and an endothermic reaction always has heat as a reactant. Okay, so that means this is your hot side and this is your cold side. Okay, so that's important because that'll help us determine which way we're shifting as we look at the various changes. So here is one situation. The mixture is heated. Okay, so if the mixture is heated, we want to shift towards the cold side. So just take a quick peek back. Which side is cold? Well, cold is on this side here. Okay, so we want to shift towards the cold side. So we want to shift to the right. Okay, so shifts to the right to use up heat. So we'll just say in brackets, cold direction. Okay. So then some NF2 is removed from the container. So a decrease in NF2. Okay, so I'm just going to write the reaction up here so we don't have to keep flipping back. Okay, and we had cold, hot, low pressure, high pressure. Okay, so we've got less of this NF2. Okay, so we want to shift to make more of it, right? So we need to shift to the right to produce more. Okay, so shifts to the right to produce NF2. We want to counteract that change. The pressure is decreased. So if the pressure is decreased, we want to counteract that. So we want to shift towards the high pressure side. So again, we're shifting to the right. Shifts to the right to increase pressure. And finally, the reaction container is cooled off. Okay, so if it's cooled off, we want to shift towards the hot side of the reaction to counteract that change. So this one will shift to the left to heat up. We'll just say in brackets, hot direction. Okay, so you can try working on worksheet 5 so that it's just a variety of different questions asking if such and such changes, which way would the reaction shift? So kind of just focusing on the 3 different changes that can take place.